So what do you think, like, how does this idea of motion came into play? So since the advent of human civilization, we always see everything like moving around us, and we find ourselves at rest, right? Since the stars and the planets and everything. So can you just brief us about this idea that how do we create motion in our daily life? Hello everyone, I'm Tanumay Banerjee. I'm currently working as a faculty at Cheenta. I am teaching physics program for several students, and today we have Panju De with us, who is currently studying at ISI Bangalore and who is also taking advanced physics level at Cheenta. So Panju, can you tell us about yourself?
Yeah, so currently I'm a student at ISI Bangalore. I'm doing my bachelor's here in physics, and I'm also a faculty at Cheenta, and I'm teaching physics, level 3 physics at Cheenta.
Okay, so Panju, you have also cracked so many other levels exam like for engineering and all. So why do you think of approaching for the physics program in your life? Like you can also go for engineering background and all.
Basically, I like physics from since my class 10, I like physics. So that was the main motivation. And when I learned coding, I was very much interested in analyzing different physical systems through simulations and stuffs like that. So that eventually led me to do a physics program here.
Okay, great. So like we want our students to do physics in certain way that they can also practically apply and understand the concepts, right? So for that we have slightly different approach from the normal theoretical approach that normally people do it. So we have also implemented several experimental softwares like Algodo and all other stuffs, so that we can also apply these things and we learn it by doing the practical experiments, right? So like since we are dealing with the motion in our current batch, so what do you think, like how does this idea of motion came into play? So since the advent of human civilization, we always see everything like moving around us, and we find ourselves at rest, right? Since the stars and the planets and everything. So can you just brief us about this idea that how do we create motion in our daily life?
So basically, in beginning, we used to see that every stars in the sky or even the sun or planets, everything moves around us, and we had an idea like every object is moving with respect to us, and we are at the center of the universe. That was one idea, and then there the Copernicus model, where it was said for the first time that we are not exactly at the center, but we are actually revolving around the sun. We have the planet Earth has its own motion throughout the space, and it's moving around sun like that. Also, earlier people used to think that to keep a body moving, we need to apply force constantly. If we don't, if we stop applying force, it will eventually come to stop. But then Newton proposed the idea that it's not actually that we need to keep on pushing the object. The thing is that there is friction, and that's why the object is coming to a rest. But if there was no friction and there was no external force, then the object will keep on moving with the same velocity. So this was main philosophical background behind Newton's laws of motions, and that sort of eventually lead us to get a good idea of motion of objects.
Yeah. So it takes quite a good amount of time for the entire understanding to build up, right? Like, and then we come to the Einstein view also, where we see that what happens is that in relative motion, we normally consider that, okay, things are added when going in opposite velocities and subtracted when in same velocities. But that Einstein and the Lorentz transformation were completely different. But that idea, can you just give a small brief about that idea also?
Yes. So initially, when we talk about relative motion of two objects, we first there was the Galilean transformation method, where we used to say that if a object is moving with some velocity v1 and another object is moving with some velocity v2, then the relative velocity of 2 with respect to 1 will be v2 minus v1 vectorically.
Right.
But then Einstein gave us his famous relativity theory, where he said that there will be no object which will be traveling with a speed greater than the speed of light. So that means the transformations that we are using in Galilean transformation system, that must be wrong. So that eventually led us to our Lorentz transformation, where we say that it's not exactly v2 minus v1, but it is v2 minus v1 multiplied with some factor, which is 1 by 1 minus v1 v2 by c square, something like that. And that keeps us that keeps in check if the relative velocity is greater than c or not, because that when we multiply with that factor, then the relative velocity cannot be greater than c. So that sort of gives us the idea of special relativity in motion.
Yeah, correct. And we can also see that as we approach the speed of light, finally, if the distance and time, they itself are changing to keep the light constant. So space and time itself are adjusting themselves to keep something constant. So that is a entirely different view of relative motion that we are in the Einstein viewpoint. So today also in classical mechanics also we see these relative motions, and we have a problem today where we can see the objects from two different frames. Let's see what the problem is. There is this monkey and this dart that this person is throwing at the monkey. So what will happen initially to the trajectory of the dart with the gravity, and after the monkey falls?
So yeah, so basically if suppose the monkey is at its position at like the monkey is fixed at its position, like it's hanging from the tree and it doesn't jump, then if the dart is fired directly at the monkey, then what will eventually happen is that since the monkey has no acceleration because it's fixed with the tree, but the dart has some acceleration g towards the toward the downwards, that will give a acceleration to the dart, and that will make the trajectory of the dart to differ from the trajectory we wanted. So it will not move in the straight line, and it will move in a parabolic trajectory, and that means that the dart will not hit the monkey while the monkey is at its position at a fixed position.
Okay.
But if I now turn off the gravity, then we can say that the dart will move in a straight line because there is no external force on the dart. So then the dart can easily dart will hit the monkey. Right. And now, if we consider a scenario where the monkey has left the tree at the same moment when the dart is fired, then what will happen is that the dart has an acceleration g in the downward direction, and the monkey, since it has left the tree, it also have an acceleration g in the downward direction. Yeah. Then I can say that relative to the monkey, the acceleration of the dart will be 0, because the monkey's acceleration will be minus g, and the dart's acceleration is also minus g. So relative to the monkey, the acceleration of the dart will be 0. That means relative to the monkey, the dart will continue to move with a constant speed and constant velocity. And we know that initially the dart's motion was towards the monkey. So with respect to the monkey, the dart will continue to move exactly in the direction of the monkey. So eventually, in the trajectory of the dart, it will hit the monkey if the monkey leaves the tree at the same moment when the dart was fired. So this shows us the importance of the relative, considering relative motion between two objects, and how it makes easier to analyze the system. We can also have done this problem by considering the parabolic motion of the dart and also the vertical motion of the monkey, and then solve two equations to find that, yeah, they reaches the point of collision at the same time, so they must hit. But when we consider relative motion, then the fact that the monkey will hit the dart eventually is very trivial to us, and that's a very important thing, that if we consider the relative motion, then the problem will be very easy to solve in this case.
Right. So in the monkey's frame of reference, what will he see? What do you think?
Yeah. So when the monkey is falling, monkey have an acceleration g downward, and the dart is also an acceleration g downward. So relative to the monkey, the acceleration of dart will be 0. And that means relative to the monkey, the dart will continue to move towards it. So it will eventually hit the monkey.
Yeah. So by part, we will just see how the cases we are considering in a practical software called Algorithm. Okay.
Yeah.
So can you present your presentation so that we can have
Yeah.
a realistic approach to view this problem?
So let's see one by one. First, we have fixed the monkey in its position, and we'll fire the object with some. We fire the object with some speed around like suppose 5 meters per second, and let's see. So what we expect is that the object, since there is gravity, the object will move in a parabolic path, and we expect that it will not be able to hit the monkey since it was directed towards the monkey, but it has some acceleration in the downwards direction, so it will not be able to hit the monkey. So let's see. So clearly, as you can see, that the object completely misses the monkey.
Yeah.
Now,
because it will be the natural instinct for monkey that he will not stay at the same position. As he sees that somebody is firing, he will just try to move his position. But actually, what is great is that he sits in his position, right? So he will be saved, right? So fine. So since monkey don't do it, so anyways, yeah.
So now let's see also the situation when there is no gravity. If there is no gravity, then that will mean that the acceleration of the object of the dart is 0. Then the motion of the dart will be always directed towards the monkey, and it will eventually hit the monkey. So let's see that. Yeah. So this clearly shows that the object will hit the monkey if there is no acceleration.
Yeah.
Now also we can try with the gravity, in presence of gravity, and let the monkey fall from its position. Then what we expect is that relative to the monkey, object have no acceleration, and initially it was directed towards the monkey. So we expect the object to hit the monkey. So let's see that in action.
Yeah.
So as you can see, there is a collision that happened here, and that means that since the monkey leaves the tree, though both the object have same acceleration, so relative to one, the other object has no acceleration, so they will be moving exactly towards each other and eventually hit.
Correct.
So yeah.
So we can try it at different velocities, so we can show the viewers that what happens even if you change the speed. Will that still hit the? So you just have to click on the boundaries so that it takes it. Yeah.
So now let's try with a different velocity. Let me increase the velocity slightly. And since the velocity only dictates the time after which the monkey and the dart will hit, but since there is no acceleration relative to one another, the final result will remain same. The final result is the dart will hit the monkey. So let's see that. Yeah. Now, as you can see, the point of collision has changed. Initially, the point of collision was somewhere about here. Now the point of collision has changed, but the dart has eventually hit the monkey.
Hit the monkey.
We can also try it with some higher velocity and with the monkey, yeah. And then the point of collision will move further higher, like this. So basically, what is going on when we are increasing the velocity, the time the dart takes to reach the monkey decreases. That means the time the monkey will fall before hitting the dart decreases, and that means the height at which the monkey hits the dart or the dart hits the monkey will increase if I increase the speed of the ball. So speed of the dart. So that's why we are seeing if I increase the speed of the dart, the height gets increasing.
So we will get different value of point of collisions, but the dart will always hit the monkey. So the only way to escape is that if the dart has specific velocity, like it's not going exactly very high speed, the monkey can just be at its own position and it can get saved. So you can show that also by attaching the monkey. So how it's getting saved.
Now we have already seen this simulation. We can try it with some higher velocity. So then what will happen is that the dart will pass very close to the monkey, but since it still has acceleration, it will not hit the monkey.
Yeah.
So like this. Now if I keep on increasing the speed of the dart, it will get closer and closer in its like trajectory, but it will not hit the monkey. Okay, okay. Maybe I should do it a little
because for
bit.
bullets, it's a very high speed. They will not get a reaction time. Okay.
Yeah. So basically, this is because I think finite size of the object. It eventually, but yeah, something like this.
The dart speed is actually very less than the bullet. Like if you're doing with bullet, so it will hit because for long time it will travel in almost straight line.
Yeah.
That is the case with dart.
So basically, the effect of acceleration we are not seeing because the speed is very high. So the time that is since the time to reach the monkey's x coordinate is very short. So the change in y direction of the velocity will be very short and will not be able to see the effect of acceleration in our motion.
So we can just increase the distance. That can happen because bullets we use for larger distances.
Yeah, like this.
Yeah.
So
so
that
we can just change the angle. Like now, how can we hit the dart? So we can just change angle a little bit. Then it will hit the dart, right? Maybe that can happen. So this is what we practically do when we're hitting with the dart. We slightly aim it above the target so that it hits the fixed target. For movable target, it will be difficult. So you can show by changing the angle also. Maybe it hits.
Yes.
See. And slightly we may be increasing the velocity also.
So let's increase the angle and keep the velocity like we had earlier. I think 7.
Very low trajectory. Okay, let's see.
Okay.
Let's see.
So, okay, still not enough, but we can keep on increasing.
So we can just increase the speed a little bit.
Yeah. So,
Yeah.
see, what we are expecting is that since this time the dart is not exactly moving towards the monkey, but it was initially aimed higher. So that's why it was able to eventually hit the monkey in its rest position.
Yeah. So we can use our physics lessons to win certain aim-based target matches also, like how to aim at perfectly, and then we can have developed that understanding to actually understanding of these motions related to each other. Right. So
Yeah.
yeah, this is a very nice problem that give a brief understanding of how we see motion and how it is exactly from rest frame, from movable frames. Right.